Okay, hi, hello everyone. Welcome to our new webinar. This webinar is organized by the GRSS Standards for Earth Observation Technical Committee. Today we have John Gilchrist from the P4001. The title of the presentation is Characterization and Calibration of Hyperspectral Imaging Devices. This is our first working group that was created by the CEO. John holds a PhD in applied physics from the University of Strathclyde. For over around 20 years, he has been a leading figure in hyperspectral imaging at ClydeHSI, and he has also chaired this standard working group. So now the floor is yours. Please go ahead.
Good day, everyone. I'm John. You might notice my colleague in the other blue shirt is also John. This is just an administrative error on our part. But we're very excited to tell you about our P4001 project. Specifically, this has been a project now that's covered over 6 years of really fantastic effort by both industry and academic colleagues who are leading specialists in the optics and characterization of hyperspectral cameras. And this encompasses the major suppliers of hyperspectral cameras, as well as their academic users across all ranges of activity. Specifically, I want to introduce Professor Torbjørn Skarli from the University of Oslo. Torbjørn is our co-chair of the P4001. And I also want to say that all of this started some years ago under the sponsorship of GRSS at IEEE, specifically by an application by Chris Darrell from LabSphere and David Allen from NIST in Gettysburg. So it's really quite an international activity encompassing all of the key players in hyperspectral imaging and hyperspectral characterization for applications ranging from remote sensing down to industrial process monitoring. And Torbjørn is a professor at the University of Oslo, a specialist in optics and optoelectronics, and also principal scientist at FFE in Oslo. And it's really a great pleasure for me to have worked so closely with Torbjørn for so long now. It's a really great what's the right word? Comradeship in this P4001 group.
Very mutual appreciation there. Yeah.
So I'd like to ask Torbjørn to review where we are in terms of the technical aspects of the standard. In terms of the administrative aspects, we have now completed all balloting, and it's with IEEE for their technical review and formatting review. So we're very close now to being published properly, and we're super pleased. Our ballot acceptance was almost 90%, which is just a stunning outcome from this. And not wanting to steal Torbjørn's thunder here, but you know, he's written a fantastic document with our colleagues of more than 120 pages, so it's a super comprehensive study. So Torbjørn, can I transfer to you now to
let me see if I can share my screen here. Do you see this?
It's not coming. There we go. Yes, perfect.
Yeah. Do you also see my mouse pointer?
No. Yes, but it's very small.
All right. We'll make the best of it. Actually, maybe I will. Yeah, we'll make the best of that. So, happy to be here. As you see from the slide, there has been an amazing number of participants representing a very wide range of types of stakeholders in hyperspectral imaging. So here we have universities, industry suppliers. We have government labs, and also user organizations for hyperspectral imaging, and also more in the machine vision. So not only geoscience, but actually all the way down to sorting of agricultural products. It has, I have to say, it's been a great experience to do this work together with all these people, and everyone involved, I think, have found this much more interesting than we thought it would be, also much more difficult and tricky than we thought it would be. And to our surprise, we have arrived at something that seems to satisfy people. So let's go ahead and see. Wait, can I change my? Yeah, we go. So long story short, this started all the way back in 2018. We had many, many meetings, many people on our various lists of voting members, or just the general email list. We have been linking up with other standards, notably the EMBA 1288 on characterization of machine vision cameras. In their case, it is camera in the sense of image sensor without a lens. And I will say that even though we are nominally hyperspectral, we are actually also doing pretty much what EMBA 1288, for those of you who know that, does for an image sensor without lens. We do more or less the same for a camera with lens and image sensor. So much of the approach is the same. We have a 120-page document. This is an old presentation. So ballots has closed. The second recirculation has closed. This is our official page, which needs substantial updating now that we actually are in the process of publishing the standard. So our scope is mainly to define a comprehensive set of characteristics for the performance of hyperspectral cameras. This necessarily involves improving on the current practice, actually, because what can we politely say here? It is an honest thing that if you buy a hyperspectral camera, well, as of last year, you would get a specification sheet, but many important properties of the camera would not be on there. And
I think it'd also be fair to say, Torbjörn, that not all suppliers use the same metrics and the same definition of a performance.
Yeah.
And for that reason, it becomes ambiguous as to the meaning of a particular thing. And that was one of the key things that was in our charter right at the very beginning, to harmonize the terminology and harmonize the parameters of characterization in a robust, defined way. And I remember very carefully that was part of the idea of John Gilchrist, who was right at the very beginning of this as well. And as a result of that, we've been able to bring this into harmony. And I apologize for jumping in there.
No, I'm very happy to do that, and please do so again when I skip over something that we need to say. Thank you, John.
Okay.
And so see if I can get, yeah. So this will improve on today's practice, and also different spec sheets have different items on them. We will also define camera-related metadata so that you can use whatever was sort of imprinted on your data by the camera to know about that and to take that into account in the exploitation of the imagery. To supplement that, we have defined some terminology, and we also outlined procedures to test cameras to find the values of these characteristics that we define, but we are not mandating specific tests procedures. We also have some introductory material, but it's the standard is not really suitable as a textbook for hyperspectral imaging. We're not trying to take that role. Maybe I'll say at this point that the standard awkwardly sits behind a paywall, and that might not be too bad because it is a specialist thing to read the standard, but we're talking about writing an overview paper which will introduce the essence of the standard in a more accessible way, and also which will be open access so that people will know what the standard is about. But if you want to get the specifics, for example, in the role as a manufacturer, then you would still have to get the original document, obviously. We'll do this, of course, in understanding with IEEE Standards Association. So there are some limitations on our range here. We define hyperspectral because we are required to define the words in our formal document to have at least 30 contiguous bands, such that the relative bandwidth is no more than 1/30. We emphasize cameras working in the so-called reflective domain, so basically reflected sunlight, which is not too deep into the UV, or this is pretty deep as it stands, and not into the thermal infrared, where sensor technology changes, and also the priorities that you would make change somewhat. So what comes outside our scope would be to what extent do you verify the specification you give? Is this just a prediction? Is it a production test, or what? And also what obligation the specification implies, whether it's a proposal or a contract, is outside our scope. We define a set of different camera types, including those that are most commonly used, as being covered by the standard, and other types of cameras are not covered, and that is particularly those based on transform or reconstruction of the spectral cube. We do not define file formats or data flow because that is covered by numerous other standards, and we're not diving into data processing or exploitation because that is not related to the camera, and the camera is the focus of our attention in this standard. We also actually made an internal list of items that we do not include because we deem them to have marginal interest. That list is not part of the standard, but it's if anyone wants to have a look, just ask John or myself. So to try to illustrate the scope, this is an informal illustration of that. So what is covered by 4001 is within the dashed line here. So those hyperspectral cameras that are in our list of covered architectures, for those we consider all these camera properties that you see here, such as and we consider the input of light into the camera aperture and the output of images and metadata. But we are not saying anything about platform or atmosphere or ground truth or exploitation or display or file format. And also there are some camera types that are outside our scope. We have to cover the range from geospatial imaging to production line inspection. We have defined 3 different use cases. So the advanced use case is for high-end applications like remote sensing, where data quality is paramount. We have calibration radiometrically and spatially, and as much metadata as possible. An intermediate case is in the lab where you have a sample that you would like to, so prototypically it is for doing reflectance mapping of samples in the lab, where data quality is still paramount, but things maybe not radiometry, only reflectance and the integrity of reflectance spectra. And in the industrial use case, we have to account for cases where we have custom systems emphasizing speed and cost effectiveness, and that only need to be just good enough. But this is, of course, a significant market, and so it is important for us to be able to serve the needs of that market. And by subdividing into different use cases, we think we can do that. Those camera architectures that we cover are illustrated here. One would be just, so what this figure that we have borrowed illustrates is just a point spectrometer, which is being raster scanned over some sample. And if you look at what does the field of view look like, the field of view is actually this pixel here in red, which is being raster scanned in 2 dimensions to cover an area. This is not so common these days, but of course the original AVRIS was working in this way, and several other airborne sensors as well. But nowadays it is the line imaging or push broom spectrometer that is most commonly used, which has a field of view consisting of one row of pixels, which are being dispersed onto a 2-dimensional image sensor, so that you get one slice of the cube with one spectral and one spatial dimension. And then the field of view looks like this, where we have a row of pixels at one given time, scanned in 1 dimension. And then another type that we also cover is the tunable filter camera, illustrated here by a filter wheel. But in the case of hyperspectral, there are many other filter technologies that are being used to create such a camera that images the whole scene 1 wavelength at a time. So of course here, the different bands in a pixel are recorded at different times. And the field of view geometrically looks like this, where we have a certain pixel spacing, both in X and Y. Finally, there is one type of spectrometers that have an array of holes instead of a slit. And the drawing is not exactly right for that. The field of view looks like this, with a light sensitive area. If you focus it, so you subsample spatially, and these are this is to give room for dispersing the light from each hole onto the image sensor. And these are of course made with great care, including to try to have a good spatial filling and to avoid contamination from one pixel to another. So these are the 4 types of cameras that we explicitly cover with the 4001 standard, but it's possible that in future versions we will cover other types of cameras or variants of these. So one important principle that we have adopted, since we want to cover these different camera technologies, is that the camera should be characterized as a black box. In other words, we look at what goes in, and we look at what goes out, but we are not assuming that we know anything about what is inside. So we also have decided that the characteristics we define shall be physical quantities applying to a black box camera. What we get from that is that we can define these quantities, and we don't have to define exactly how to test them, because they exist as physical quantities. And that allows us to give the freedom to the practitioners to use their equipment and to their preferences as far as it goes. But of course, you have to, in the end, measure this quantity. we will recognize very carefully that hyperspectral imaging is actually more spectroscopy than imaging, as has been pointed out by NASA JPL for like decades, because we're not looking so much for spatial contrast in different bands. We are looking for spectra in different spatial pixels. And so the integrity of the spectrum in a pixel is of great importance here. And finally, a principle is that we should express the actual performance. So we will include worst case values. We will require that all elements of the spec should be achieved at the same time, and so on. So to minimize the risk of disappointment on the part of the user. So how about this black box camera? It receives light, it outputs data, and we don't know anything about the internals. And so what are the characteristics for a black box camera? What is a minimal, so necessary and sufficient set of characteristics for that, so that we can cover, as far as possible, all aspects of performance, and also to make that comparable between different camera types? So the answer to this was not really known when we started. The question was not even known, I would say. So, and that is to some extent much of the reason why we had all these meetings, because we were chasing our own tail for a while, figuring this out. We actually had to define some new characteristics, and I'll show you some of those. So here is just a little taste of what is the theory then for a black box camera. Gets a little bit esoteric here, but the signal is a spectral radiance, which depends on angle of arrival and on wavelength. And it, in principle, also depends on where in the entrance aperture it arrives, and it may vary with time. So this is our input, and our output is, in our thinking, it is a photoelectron count. Now, you may argue, of course, that cameras, a black box camera, may output a digital value and not a photoelectron count. But it turns out that if you know the photon transfer technique, it is possible, under reasonable assumptions, to test the camera using a variable light level, and to back out the scaling factor between whatever value is output by the camera and the photoelectron count that was the basic signal inside the image sensor. Then the camera selects some of this light to become part of the signal in a pixel. It will select within a band of wavelengths, within a cone of arrival angles corresponding to a pixel, within an area in the entrance pupil plane corresponding to the hole where the light enters, and within the integration time. So this is a very formalistic way of describing what the camera does. And it gets worse when you see that the photoelectron count is, of course, then or I don't know if it's of course, but it's a weighted integral over wavelength, angle of arrival, position of arrival, and time. But of course, this quickly gets translated back to something familiar, which is an input signal, the settings of integration time and bandwidth, photon energy needs to be taken into account, and then it is the light collection by the camera and the losses in the camera. But this arrow here replaces a little bit of derivation so that we can rigorously say what we mean by these A omega and T and eta. And that actually brings out some assumptions that we are not always explicit about. And also there is it turns out that if the camera employs resampling, you may ask what is then the photoelectron count? But it turns out that we can then replace the black box camera with resampling with an equivalent black box camera that has different properties, but no resampling. And we can apply the same model through that approach to a resampling-based camera. So here is our signal model, and we note that these quantities here are inside the black box. So this is the first of several examples of our approach here, because it turns out after a lot of thinking that we can, and we have to replace these by a single number, because they act as a product looking from outside the black box. So this is a place where I've stuck my head out and said that let's define this as a quantity, and we call it A star, and it is essentially the pixel area of an equivalent lossless camera that has roughly a f1 optics on the image side. You can read about that at length in a paper that sort of underlies this quantity that is now part of the standard that's coming out. Another is the readout noise, where we need some number to represent that, and the noise equivalent spectral radiance is one way it's often done in hyperspectral, but this has some kind of wavelength dependence through the photon energy that's not really helping us get comparable measures. So it turns out we can, in MBAT 1288, they normalize the read noise by taking the actual read noise divided by the pixel area. We can do the same thing by taking the read noise of the image sensor divided by the A star. So this gives us the physical interpretation of this is the noise equivalent radiance dose, which fittingly is nerd. So another example of quantity that we need is the dynamic range, which in the case of a single pixel, it will be the ratio that the pixel of the image sensor can take between its noise floor and its saturation level. And depending on the losses in the camera, these levels will vary with wavelength. But if now we're looking at a spectrum of light, such as a daylight spectrum shining on a white or gray object, then as you vary the light level, you will scale this spectrum up or down, and you may hit saturation in one band when you scale it up, and you may hit the noise floor in another band when you scale it down. So the accessible dynamic range is less than that of a single pixel. And if you change the light level, it may be different. So the standard requires a specification of dynamic range together with a corresponding illuminance spectrum. Another example, which I think is very important, is how do you specify resolution? So we know pixel count and ground sampling distance, and we know that it doesn't really tell us what the resolution is. And of course, resolution isn't really definable even, but we have established this by saying that let us define, so we have put some work into defining a robust measure of peak width for, in this illustrates a spectral response function, but we have the same for the spatial dimension in 2D. We can define a peak width, and we know the spectral range or the width of the field of view, and we can just take the field of view, divide by the peak width, and that will be our equivalent number of pixels or effective pixel count. So I think we call it equivalent actually. So this is now a much more reasonable, a realistic number for the number of pixels or bands that you actually resolve, even though resolution is still undefinable. But there are a couple of papers that we think are useful that came out of this work. Yeah, sorry, I forgot to bring this up. So we have a useful definition of resolution. Another example is co-registration of bands, where since we do spectroscopy, we care that in a given pixel, such as the center in the example here, we would like, so this illustrates a contour map of the sensitivity distribution for that pixel. So we would like to think that, or we normally think that all bands in a given pixel have the same footprint in the scene, illustrated by this contour map here. And for one band, such as the blue band here, that may be true, but maybe due to aberrations, another band is a little bit offset. or it's a little bit defocused, or has a different shape of its point spread function. And so to account for this in a quantitative way, it turns out that by integrating the difference between these pixel sampling point spread functions, we get a metric that actually is an upper bound on the error in reflectance that you estimate from this image. And by doing the average and worst case overall band pairs, we get a nice or comprehensive specification of co-registration error that relates to reflectance mapping, and which generalizes the SMILE and keystone quantities that people often quote. To test cameras, we will need 4 test setups: spatial resolution and field of view, spectral resolution and wavelength calibration, radiometric calibration, and stray light. And these are actually conventional measurements that most players will be able to do already. But because we do spectroscopy, we need to add one element, and that is to characterize the shape of the spectral and spatial response functions. Since we care deeply about the integrity of the spectrum, we cannot avoid doing that for our standard. So, but of course, this may be necessary in some cases, but for example, in a production test, one might do simplified tests as long as you know that you have a handle on the variability of your product. So this illustrates what a lab might look like, and in principle, you're shining light onto the line-shaped field of view of a push broom sensor, and we are not mandating a full mapping of the SPSF. We're requiring a scan in the X and the Y directions of the pixel sampling point spread function. So this is what that might look like if you measure. So this is a line spread function and the along track and a cross track dimensions. And when you multiply those together, you get an estimate of the point spread function for that pixel. And if you have a different pixel, you can look at the difference between those two, and you can integrate this difference between them to get one point in a matrix that gives us the co-registration error metric for each band pair, obviously a symmetric matrix. In the radiometric test, you need to vary the light level and characterize the noise as a function of light level to do a photon transfer measurement, which is a very informative way of looking at things like saturation level, scaling factor to photoelectrons, readout noise, and so on. And finally, stray light testing. We outline a simplified as possible way to characterize stray light in hyperspectral cameras by basically looking at a brightly lit white surface with a gap where we have no light. And so if you see some light there in the image, this is obviously stray light, which we can characterize as an apparent reflectance where there is actually no reflected light. And we can do the same thing in the spectral dimension by blocking out a part of the spectrum and looking at the spectrum with or without the blocking. And then again, the stray light can be expressed as an apparent reflectance in the spectral range where the stray light is blocked. As you may understand, this is not giving a full coverage of all the properties of the stray light, and it's not sufficient to correct for stray light in the data, but it will give an indication in the specification as to how large or small the effect of stray light is on the signal. So to sum it up, this is just a flash of our list of performance characteristics. There's about more than 40 of them altogether. Some are obvious, like spectral range or number of bands, and some are less obvious, such as the dynamic range or co-registration. And we also have a mock data sheet, how that might look, but we're not requiring a particular formatting of the data sheet. Yeah, so I pull through the complete list of parameters here in case you have questions to some of this. So characteristics, bad pixel polarization dependence, right? We also have no less than 60 metadata items related to the camera. But I should mention that on the right column here, we have the machine vision, lab, and geospatial use cases. And so M says means mandated, O means optional, and R means recommended. And so we are not mandating a very extensive set of metadata for industrial use, but for remote sensing, we are mandating or recommending an extensive set of metadata. Some of these types of metadata, like we had to define new performance characteristics, some metadata types are also new, but we believe that they have potential to aid extraction of information from image data. So to conclude, this it says about X months. I don't know exactly what the X is, but maybe it is on the order of 2. We hope that it will be widely used in the hyperspectral community. For example, to set up design requirements for cameras or data sheets or in procurement processes. And from John, Chris, and myself in the leadership team, we will contribute to outreach and training to help people begin to use the standard. It's also likely that there will be a future version because inevitably there will be some things that are not clear or that need to be changed or added in the standard once we gain experience, because to be honest, I think not a single camera has been fully characterized according to this standard as of today. And on that point, I will, we will contribute to training and this future revision, And on the final point of testing cameras, I will add for myself that if anyone interested in lending or bringing their camera here to Oslo, Norway, I'd be happy to test some of the finer points here, particularly co-registration. But with that, I will stop my presentation for now, and we'll see if there are any questions.
Yeah. I think it's also important to say, Torbjørn, that the idea is that customers can request to have their a data sheet that demonstrates the compliance with P4001, although it's not a mandatory thing. It's a bit like IMPA 1288 for machine vision cameras, that a manufacturer may be able to offer that allows proper comparison and so on. And there's a question in the chat about, is this applicable to airborne and UAV solutions? And the answer is absolutely yes. So we've been really independent. We've really looked at the case studies for the geosciences, the laboratory inspection and industrial inspection activities, and the applicability of the camera data is the key thing, and that means a proper characterization to ensure that what you get is going to solve the problem correctly, deal with the problem correctly in a really unambiguous way. Another question is about the paywall. We're not, Torbjørn and I are advocates of open source. And that's really a question for IEEE themselves to answer.
This is basically how standards organizations fund their operations, because there is a staff of permanent employees at IEEE who support us creating a standard. So, but there is a program from the IEEE Standards Association to have sponsorship for open access to standards, but that would require some players with a budget here to come together to pay for open access to IEEE. And if anyone are interested in pitching in, I think you should contact John, and he can maybe see if we can arrange open access to the standard.
Yeah, it requires I'm going to say first that we have investigated this, and it requires a somewhat deep pocket to meet the IEEE requirements to remove it from a paywall.
I will say also though that if you get the standard and 120 pages lands on your desk, I had one comment that this document is dense, which really is, and so I think that if we over the course of the summer perhaps are able to write up a summary paper, then I think many people will be well helped with that. The aim is roughly to inform people who are reading datasheets created according to this standard, to let them know what these quantities are saying. And I think that will cover the needs for most people, because then also you know what kind of information to ask for if it happens to be missing from a given datasheet.
I think that Siri Yoda has a question. Please, can you unmute by yourself, Siri?
Siri Yoda was making the comment that you know, a summary document could be available, and in fact, I've written a summary document already, and Torbjörn and I are thinking about how can we make that into something in alignment with IEEE that does not conflict with IEEE and the standard, but becomes an informative document that that normal people can see without restriction. And it's almost like it would be a conference paper or something like this type
I'm aiming
idea.
I'm aiming for open access journal paper.
Yes, exactly. Exactly. So that's a discussion that we're having just now, and so that people can get a good idea of what the standard is, what is in the standard, what's relevant to them or not relevant to them. The key thing in the end is to make robust, repeatable, reliable data for your application, and the key thing for that is to understand how the behavior of your camera is, and does it meet the requirements that you have to operate with. It's not another question. Can we release a draft version? The answer is no. The working group membership had access to the drafts, and the voting ballot group had access to the drafts. We're not allowed to distribute drafts outside of that group. And now that balloting is closed, it's with IEEE staff for their review and administrative tidy-ups and so on.
Okay, thank you very much for this very interesting work and this very interesting talk. I think that we have time for a few more questions, so please don't be shy, attendees. I have a question. Now, what are your plans for dissemination? So to foster the usability of the standard, I think maybe this is the next step, thinking outreach activities and dissemination. What are your thoughts about that?
Over the last several years, we've been regularly disseminating the progress of the standard development work at a range of conferences, including SPIE, Photonics West, DCS, Photonics Europe, and others. That's also included, will include this summer at IGARS in Australia, and also and Sirijoda Khalsa has very kindly volunteered to give the presentation, on
I
our
will
behalf.
be presenting, unfortunately, online only at the CalCon conference next week in Utah.
Yes.
So yeah, we'll be around at conferences talking about this, and maybe it can also be shaped into a short course, though we have no concrete plans about that right now, but it seems to me that this could be one good channel for outreach.
Yes. Well, you know, we have really taken the idea of dissemination very seriously right from the very beginning, and that's also been one of the joys of doing this, because the feedback from that dissemination activity has been very helpful in developing the standard and bringing other people on board as specialists in their areas to help with this. We've got to say that we have a group of about 260 nominal people, of which almost 40 people are the die-hard regulars every single month for the last almost 6 years, and it's been tremendous. And you know, I can only express on behalf of the leadership team our sincere and deep thanks to them, because without those detailed reviews, and you know, I'm thinking particularly we have one colleague, Ray Sofer, has done an absolutely, and Dave Perry have both done unbelievably detailed reviews with you know, to the level of a comma should be here and a dot should be there, and so on. And Torbjörn and I see this document every day, and we become blind to all these things. And it's just wonderful to have those really nice, wonderful people to help, and also to say thank you to the industrial people that have participated in this, from some, not all, but some of the hyperspectral camera suppliers, and that's been very encouraging. The fact that they were able to work so nicely
surprisingly
together
many have been
in a collegiate way.
And for CalCon, I made this list. May I share for a moment? But this is more from my own perspective. There is a fair number of papers out there that will be in the recording here that you can look up, which cover parts of the standard, but these are sort of, they become one of the 40 elements of the standard. So at this time there is no complete overview out in the literature of what is in the standard, but we also have, of course, several conference publications that you will find containing essentially the material that we presented here today.
Okay, that's great. So thank you very much for this very, very nice work. Congratulations. And if there are no more questions, I think we can go to the end of this webinar. Okay.
Yeah, it's funny now, Hugo. The end of this project, the impending end of this project means what will Torbjörn and I do in the morning, every morning to...
that is not clear at all.
Yes, not clear. We need to find a new project, Torbjörn.
Yeah. I'm sure there will be complaints coming in pretty soon that things don't work or are difficult to understand. So at some point this will start up again, and if we if we think we can take it, we might run for these leadership positions again.
Yes. The wonderful thing is that this is the first time that there has been a comprehensive, systematic comprehensive, systematic way of looking at hyperspectral cameras. And that's a tremendous output, I think, from this project. And version 1 of the standard is coming. Torbjörn is completely right. It will evolve now in the fullness of time as people begin to use it and technologies change and so on and so forth. And other people want to see other metrics and so forth. It will develop in the same way that this will be a living thing in the future, exactly like ENVA 1288 is, which I now think is on version 4 something. So yeah, I think there's a lot of work for Torbjörn and me and others that will keep us out of trouble.
Okay, thank you very much, and have a wonderful day.
Thank you.
Okay, thank you everyone.